Hello and welcome. I'm Adam with Push the Envelope, the channel that gives you everything artificial intelligence and machine learning. Today we are going to be looking at a brand new series that I put together, and that is the Building a Neural Network from Scratch series. So this series is going to consist of 3 videos, and by the end of it we are going to hand make our own neural network, not using TensorFlow or Keras or any of the other pre-built packages, but using NumPy so that we get a better understanding of what actually goes behind a neural network and how do they actually work. Now, unfortunately, we can't jump right into building the neural network. There's a lot of underlying principles that we need to understand, and by far the biggest is gradient descent. So gradient descent is the building block for machine learning, and especially deep learning. So these first 2 videos are going to give first a dive into the theory and math behind gradient descent. I'm going to try to keep it as simple as possible so that anyone can really understand it. And then the second video is going to look at implementing gradient descent in Python. Now, once we do that, we will take everything we learned from those first 2 videos and incorporate that into a shallow neural network. So I can't wait to start. I've had a lot of fun putting this together. So without further ado, let's jump right into the first video. Today we're going to be talking about the theory of gradient descent. So let's get started. So I'm going to introduce gradient descent in a little bit of a different way. I'm going to just start right off with an example problem. So let's pretend we have some x input, and x consists of 2 components, so 2 features for x, and we'll call those x1 and x2. And what we're trying to do is we're trying to take these 2 input features and map them to an output, and this output will be y. Now for those who haven't seen y hat before, y hat refers to whatever your predicted values are for the actual value of y. And right off the bat, what we need to do is we need to pass those input features to an input layer. And now once we have those 2 nodes for our 2 input features, we need to map those to our final output, which will look something like this. So 2 nodes going to a single node. Now, there's a lot of underlying things that we kind of glossed over, so let's go back and fill in some of those. And the first is we have 2 nodes that need to be mapped to an output, and we do that using weights. So we're going to be taking our inputs, multiplying them by weights, and that will give us our output for the single node. Also, we have something called bias that we can add in, and this will just be added to those first 2 equations to give us the input for the output layer. And the very last thing, part of the output layer, is the activation function. This is just some function that you define to map your inputs for the output layer to the output values of y. All of that sounds fairly confusing, but trust me, we'll deep dive into this. It's not rocket science. It's actually fairly easy to comprehend once you get an idea and see an example problem run through. Now, the training process consists of 2 parts. First is you're going to be feeding forward your data to get your y hat results. So you're feeding your inputs to get some predicted values. And once you get your predicted values, you want to adjust your network to make your predictions better. So you want to learn from whatever you predicted and whatever the real values are in order to adjust your network and make your predictions more accurate. And that part is called backpropagation. So backpropagation is just going to send a signal backwards through your network in order to adjust your weights and biases to be better mapped to the actual y values. Okay, there's a lot going on here, so let's start to break this apart. First thing we're going to look at, we are going to take a look at the activation function. In this case, I'm going to use sigmoid, so that's this little symbol right here. Now there's various other activation functions you could use, things like tanh or ReLU. Sigmoid is one of the most common ones, so I'm just going to use that one here, and that is equal to this equation, 1 over 1 plus e to the negative x. In this case, since our activation function is on the second half of our diagram up top there, the x value that we'll be passing into sigmoid will be that red node there. So whatever the result is at that red node will be passed through the activation function to give us our final predictions. Now using that, we can come up with an equation for y hat. And Now that we have the activation function, we'll need to know what that first half of the network is equal to. And again, that boils down to a very simple equation. We are taking our inputs, we are multiplying them by their respective weights, and then we're adding a bias. And that's it, guys. It's super simple. There's not much here, and it's super easy to comprehend. Obviously, it does get harder when you have more inputs and when you're talking about more complex problems, but fundamentally, this is what we're doing. We're just taking our inputs, multiplying them by weights, and adding some bias. Now, this gives us the first half of the network, and as you remember, that second half is the activation function, so we are just going to be feeding that into sigmoid. Now, that gives us the feed forward part of the training process. And now what we'd like to do is figure out how far off were our predictions from our true values that we have. If you're using supervised learning, then you have the real values of y that you can compare the predicted values to. And we use something called loss in order to determine a numerical value of how far off we are. And for this case, I am going to use log loss. And essentially, if we use log loss here, we are going to be doing logistic regression within this network. So I'm going to kind of gloss over this equation, but just trust me, this is the equation for log loss. I don't want to focus too much into it. You could use other ones like mean squared error, and you would be doing things like linear regression. There's a whole bunch out there. I don't want to focus too much on the loss equation, but this is the equation, and then we can take this a step further in order to do our backpropagation. So in order to do backpropagation, we need to come up with something that will let the weights and the bias know how much they need to change by. So actually, if we go ahead and take our loss function and we break it down a little bit, so we're going to be looking at the derivatives with respect to the weights and respect to the bias. And again, I'm going to kind of gloss over this math part, but this is what the weight 1 derivative with respect to weight 1 will look like. And it's basically just taking our x1s and multiplying it by the difference in our predictions versus the outputs. Weight 2 is going to look the same, except we're taking the x2 or the second features, and bias is going to look the same, but we're just going to take the difference between the outputs and the actual predicted values. Now, there's a lot of math here. What does any of this actually mean? I will show you a diagram. Hopefully that will help explain it a little bit better. And so we're going to look at two different parabolas here. Now, what are these parabolas trying to show? If you think of your loss function as a bowl, and at the very middle of your bowl is the lowest point that you can possibly go. And I took this 3D bowl and I cut it right down the center on the x-axis and right down the center on the y-axis. And that's what you're seeing here. Left is the x-axis, right is the y-axis. And let's pretend that we have a ball that is somewhere in this bowl, and it's located where these two are. So at any point on this parabola, we are going to be able to find the slope of this ball and see how far or how fast it's rolling down, and if it's getting to a point where it's not rolling anymore. And so we can do that by finding this line right here, this red line. And if you know anything about finding this slope, it will be the gradient or the derivatives that we just took in a few slides ago. So those derivatives are going to tell us essentially what the slope is at the point we are at right now. And what we're trying to do with gradient descent is we are trying to get to this green line right here where there is no slope. We are at the very bottom, and the ball essentially wouldn't be moving anymore. And that's all it is. That is gradient descent. It's just trying to descend down this gradient in order to get to the lowest point with respect to all axes. Okay, now that we know that, let's return back to our diagram. And now that we've got the derivatives and we know what we're doing with them, now we need to update our weights and biases with the information that we just got. So we're going to take weight 1, and we are going to subtract a learning rate. So the learning rate is just how fast you're going to descend down that gradient, how fast you're going to converge on your answer. And that's going to be multiplied by the derivative that we just took with respect to whatever weight or bias you're looking at. Now let's do a deep dive of what the learning rate actually is to kind of give you an example, and you can see the difference between higher and lower learning rates. So if we go back to two identical graphs here, and we have our ball somewhere up towards the top. On the left, you can see we have a low learning rate. On the right, you can see we have a high learning rate. And now when we take one step, so this is one iteration through our network, so one feed forward and back propagation, our weights are going to be adjusted. And as you can see, with a low learning rate, our ball moved gradually down, moved a little bit. Now on the right hand side, with a high learning rate, it moved a lot, and in fact it actually jumped over the minimum that we're looking for. Now it is lower down the curve than the original point, but again, it's not necessarily where we wanted it to go. So we're going to take another step, and you can see on the left hand side we're slowly going down the slope to get to the bottom, and on the right it took another step, again jumped to the other side, but we are approaching the bottom. And we're just going to complete that out. So as you can see on the left hand side, we made it all the way to the very bottom. Now on the right hand side, we kind of hit a limit. And so it got to this lowest point, and it never really could go any lower, so it thinks that this is the lowest point. Now that is the problem when you use a higher learning rate, is you may not hit the very bottom or the very optimal solution, which may be fine depending on whatever problem you're using. And then also the trade-off is if you use a lower learning rate, it's going to require more iterations through your data, more computation time, and it's just going to be more expensive. So trade-offs between the two, typically learning rates are set to something like 0.01 or 0.001, but again, it's sort of problem specific based on whatever use case you're doing. Okay, so now returning back to this, now we can update weight 2. Weight 2 is going to be the same equation. So learning rate times the derivative with respect to weight 2. And bias is, again, same thing. Bias minus the learning rate times the derivative with respect to the bias. And that's it. Now we've adjusted our weights, and that is all gradient descent is. Again, it's not really hard, guys. This is as simple as it can get. Now, again, as the problem becomes more complex and we start adding other layers in here, that is where the chain rule applies and the derivatives get harder. But at its simplest, this is gradient descent, and this is how easy it is. Now, if we go back to our original diagram, you can see we have feed forward. And again, feed forward is just pushing your data through this network and getting our predicted values for y. And as you remember, once we get those predicted values for y, we can have some loss function to figure out how far off we are. We can use backpropagation to find the derivatives with respect to the weights and bias. And we can go back and update those weights and bias depending on whatever our learning rate is. That depends on how much we increment them by. And that is a training cycle. That is a single training cycle. It's moving through the feed forward process and then doing back propagation to update everything. And when you start training a model, you are going to do this for however many epochs you want. And epochs is just however many iterations you want to go through feed forwarding and back propagation. So if I do this for 1,000 epochs, I am going to adjust my weights 1,000 times using this process right here. And that's it, guys. That is gradient descent. It doesn't have to be too complex. This is a fairly simple problem, I'll admit. Now, if you start adding more features and more layers and more neurons, it does get more complex, and you have to use things like the chain rule in order to find your derivatives, and there's a lot more steps you have to do. However, at the core, this is what gradient descent is, and it's fairly easy to implement. So that's what we're going to be doing next video. is we're going to be taking everything we did here and we're just going to be implementing it in Python to see how we can use this to train a very simple model. And then we're going to take that one step further and we're going to make our own neural network from it in the video after that. So definitely stay tuned. If you got anything from this video, please hit that like button and definitely subscribe to the channel if you got anything out of this and you want more content. As always, thank you, and I'll see you in the next video.